You already know what a limit is. This lesson is the toolkit for actually finding one when the obvious move fails. Take this limit as x approaches 3. The obvious move is to plug in, but substitute 3 and the top becomes 0 and the bottom becomes 0. 0 over 0, not a number, but a warning light. This form is indeterminate. Do some work. So here's the whole strategy. Always try substitution first. If it hands you a clean number, you're finished. That's the limit. But if it hands you an indeterminate form, 0 over 0, infinity over infinity, infinity minus infinity, then you reach for a tool. There are 4 worth mastering. Factor and cancel. Rationalize with a conjugate. The squeeze theorem, and a short list of standard limits. Let's pick them up one at a time. Tool 1 is the workhorse for 0 over 0 with polynomials. If the top and bottom share the factor that's vanishing, factor it out and cancel it away. The top is a difference of squares. X squared minus 9 is x minus 3 times x plus 3. And there it is, an x minus 3 sitting on top and on the bottom. Because x is near 3 but never equal to 3. That shared factor is non-zero, so we can cancel it. Strike it out, top and bottom. What survives is just x plus 3. A clean line, no trouble anywhere. Now substitution is safe. 3 plus 3 is 6. The limit is 6. And the graph shows what the algebra did. Everywhere. Except x equals 3, the function is the line x plus 3, with a single open hole at 3. Both sides march straight to the height 6. That's the limit. Tool 2 is for when a square root blocks the cancellation. Here's a classic. The limit as x approaches 0 of root x plus 1 minus 1 all over x. Substitute 0. Root 1 is 1. So the top is 0 and the bottom is 0. 0 over 0 again. But this time that root leaves nothing obvious to factor. Here's the move. Multiply top and bottom by the conjugate. The same expression with the sign flipped. Root x plus 1 plus 1. That's multiplying by 1. So nothing changes. But watch the top. The top is now a difference of squares. Root x plus 1 squared minus 1 squared. The root disappears. That's x plus 1 minus 1, which is just x. And now the magic. There's an x on top and an x on the bottom. Cancel them and the trouble is gone. Substitute 0 at last. Root 1 is 1. So the denominator is 1 plus 1, 2. The limit is 1/2. And the picture confirms it. Undefined at 0, yet from both sides the curve homes in on 1/2. Exactly the value the algebra promised. Tool 3 is the most beautiful of the lot. The squeeze theorem, also called the sandwich theorem. The idea is pure geometry. Trap your function between two others. If the two outer functions both head to the same value L at a point, the one caught in the middle has nowhere else to go. It's squeezed to L as well. Here's the example that shows why we need it. Take x squared times sine of 1 over x as x approaches 0. As x shrinks, 1 over x explodes. So the sign oscillates infinitely fast between -1 and 1. Nothing to plug in, nothing to factor. But here's the key. Sine of anything, always, sits between -1 and 1. Multiply that fact through by x squared, which is never negative. And the whole messy function is trapped between minus x squared and plus x squared. Draw all three. In blue, the two envelopes, x squared on top, its mirror minus x squared below. And in gold, the wild function, thrashing between them, faster and faster as it nears the center. Now watch the trap close. As x slides towards 0, both envelopes are pulled down to the origin, dragging the gold function with them. It cannot escape. So the limit is 0, forced by the squeeze. No factoring, substitution, or conjugate could have touched that limit. The squeeze got it in one clean stroke. The squeeze earns its keep by proving the single most important limit in calculus. As x approaches 0, sin x over x approaches 1. It looks like 0 over 0. Yet here's the picture that proves the answer is exactly 1. Draw a unit circle, radius 1, and mark a small angle x in radians. The radius meets the circle at a point P, and this rho segment, the height of P, has length exactly sin x. Now stand a tangent line up at A and run the radius out to meet it at T. By definition, that green height is exactly tan x. Three regions now sit nested inside one another. Compare their areas. The inner triangle, 1 half sin x. The Paisley sector, 1 half x. That clean formula is exactly why we insist on radians. And the outer triangle, 1 half tan x. Because each region contains the 1 before it. Their areas line up in order. Cancel the 1 half from every term, and you get a gorgeous sandwich. Sin x, less than tan x. Now divide the whole chain by sin x, which is positive for small x. The middle becomes x over sin x, and tan x over sin x is 1 over cosine x. Flip everything over, which reverses the inequalities, and we've boxed sin x over x snugly between cosine x and 1. And now the squeeze finishes it. As x goes to 0, cosine x goes to 1, and the 1 on the right is already 1. Both walls close on 1, so the thing trapped between them, sin x over x, is forced to 1. Proven. That one limit brings a whole family of standard results with it, worth committing to memory, each one taking 0 over 0 to a clean number. Every angle in radians. Sin x over x, e to the x minus 1 over x, and the log limit all go to 1. 1 minus cosine x over x goes to 0, and 1 plus 1 over n to the n climbs to e. Meet these often enough, and they become instinct. One more tool for limits as x runs off to infinity. For a ratio of polynomials, substituting infinity gives infinity over infinity, another indeterminate form. The fix is neat. Divide every single term, top and bottom, by the highest power of x in sight. Here that's x squared. The expression is unchanged. But now every piece is either a constant or something over a power of x. And now the magic of large x, 2 over x and 1 over x squared, both shrink to nothing as x explodes, leaving 3 over 1, the ratio of the leading coefficients. The limit is 3. On the graph, the curve settles onto the line y equals 3, a horizontal asymptote it hugs ever closer as x marches right. That flattening is the limit, seen directly. Let's put the standard sign limit to work. First, the limit as x approaches 0 of sine of 3x over x. Substituting gives 0 over 0, but this is so close to our friend sin x over x. The standard form needs the same thing inside the sign as underneath. So, multiply and divide by 3. Now it's sin 3x over 3x, which goes to 1 times that leftover 3. As x goes to 0, 3x also goes to 0. So sin 3x over 3x is exactly 1. 1 times 3 is 3. The limit is 3. Now a tougher one, sin 5x over sin 2x. Again, 0 over 0, and again the trick is to conjure the standard form on the top and on the bottom. Split it into 3 factors. Sin 5x over 5x, standard. Its partner, 2x over sin 2x, also standard. And what's left? 5x over 2x is just the constant 5 halves. Take the limit. The first factor tends to 1. The second tends to 1, and the constant 5 halves just sits there. 1 times 5 halves. The limit is 5 over 2. Your turn. Here's a limit as x approaches 3. X squared minus x minus 6 over x minus 3. Substitute and you land on 0 over 0. Decide which tool fits, work it out. Then come back. Pause now. It's a polynomial over a polynomial. So tool 1, factor and cancel. The top factors as x minus 3 times x plus 2. Check. They multiply back to x squared minus x minus 6. That x minus 3 cancels against the bottom, leaving x plus 2. Substitute 3. 3 plus 2 is 5. The limit is 5. Spot the shared factor. Cancel it. Substitute. You've got the whole rhythm of this topic. Trap 1. The big one. Writing 0 over 0 equals 1 or 0. It equals nothing. It's a signal to do work. Factor, rationalize, or reshape. Trap 2. Infinity minus infinity and 0 times infinity are also indeterminate, not 0. Rearrange them first into a single fraction or a conjugate until they become a 0 over 0 you can handle. Trap 3. The sign limit only equals 1 when the angle is in radians and tending to 0. Match the standard form before you apply it. And trap 4. Only cancel a factor the top and bottom genuinely share. Striking a term that isn't a common factor quietly changes the problem and hands you a wrong answer. Let's lock it in. Always substitute first. A number means you're done. An indeterminate form means pick a tool. For 0 over 0, factor and cancel the shared piece. When a root blocks you, multiply by the conjugate to clear it. When a function is trapped between to that agree, squeeze it. And remember the crown jewel. Sin x over x goes to 1 with its family of standard limits, and heading to infinity, divide by the highest power and let the small terms die. Master these, and no limit on the page stays indeterminate for long.